And I said here that this distance was h over sine theta. Now, why is that true? Well, so if you remember, of course, sine theta is opposite over hypotenuse. Now, this is the theta here. So the opposite is the h. So we have sine theta equals h over what? Well, the hypotenuse is the distance. This is the new distance that we have to move it when we have the ramp. So I'm going to call this, I'm going to say distance. This is the thing that we're solving for. Now, you just have to solve algebraically. What does that come out to be? So if I'll tell you what, I'm going to replace the distance with just a d to make this simpler. So that distance d, that's this whole distance. That's the size of the hypotenuse there. So if I multiply both sides here by d, I get d sine theta equals h. Divide both sides by sine theta, I get d equals h over sine theta. And that's exactly what I said here, that the distance will increase from h to h over sine theta. So your mechanical advantage is essentially 1 over sine theta, because you're able to change the mg to mg sine theta, but that comes at the expense of a longer distance, h over sine theta. That's what the ramp does. Now, it's worth noting, and this is the no free lunch thing I was telling you, the work is the same in both cases. The amount of work that you do is the same in both cases, because here, the amount of work, you remember this work energy idea that the work is equal to the change in energy. Well, in this case here, the work is mgh. That would be the change in gravitational potential energy here. You could also say it's the force times the distance, because this is the force you're having to apply, the distance you're having to apply it over is h. Two different ways to see that. Work equals mgh. Well, here, in this case, the work is, well, you're applying a smaller force over a longer distance. So if your work, so one way to see this was that work is force times distance. The force was the mg, the distance was the h in that case. So if you're doing the same thing here, well, work equals force times distance. The force now here is mg sine theta, and the distance is h over sine theta. So the sine thetas cancel, and that leaves you with mgh. That's what it boils down to, which is the same as this mgh here. So the work is going to be the same in both cases. You don't get any free lunch. You just trade off. You exchange distance. You accept a longer distance in order to achieve a lesser force. That's the mechanical advantage. Okay, so let's talk about the lever now. So with the lever, here I said same work. I'm going to also say same torque here, and I'm going to finish off my parentheses there. So for the lever, what you're doing is you are force decreases from whatever the initial force, whatever a given baseline force. I'll explain more in a second, but so I'm going to say from F, I'll just say F1 to L1 over L2 F1, lever arm increases from L1 to L2. Now, the specific context in which I'm talking about this is you're comparing two things. And you're comparing this diagram I've drawn here to another diagram in which the lever arms are the same. So you start out with a baseline situation here where you have the fulcrum right in the middle here. And if you've got a certain force going down here, and this is a distance of L1, and this is also distance of L1, then you would have to balance it with exactly the same amount of force. Now suppose you have an elephant or a hippo sitting on this end of the ramp. You're not going to be able to exert enough force at this distance of L1 in order to compensate for that force that's being exerted here. So what the strategy is going to increase the lever arm. So you're comparing this, you compare this ... to this, where you have the same picture with the length 1 and the force 1, and this is what you want to cancel out. But now you increase the lever arm a large amount. And so this distance, just for, I was going to say for consistency, I want to draw this looking essentially the same as what I had there. So now you can apply a smaller force. Now, why is it okay to apply a smaller force? Well, the point is that for this to be balanced, you need the same torque. So to balance, you need the same torque in both cases, in this case and in this case. Now, you remember the torque, so this would be torque, in this case would be, and would be an F1 here. The torque in both cases would be, well, in this case it would be L1 F1. We're assuming we're applying the forces straight down, so there doesn't have to be a sine theta in there. Here the torque is L2 F2, and those torques have to be the same. So I could call this torque 1, I could call this torque 2. And so if torque 1 has to equal torque 2, I'll actually write it in the other order, torque 2 equals torque 1, then this says that L2 F2 equals L1 F1, and then I divide both sides by L2, and so this says F2, the force I have to apply now, is L1 over L2 F1. And so that's where this comes from, that the force decreases when I increase the lever arm. And it's obvious that what's accomplishing that is to increase the lever arm to L2. That's what I'm assuming that I'm doing here. So once again, you get mechanical advantage. You're able to apply a smaller force in order to get this to move. Of course, in order to get your seesaw to go to a certain angle, in order to get this to rotate up a certain amount, you have to apply that force over a longer distance here than you did here. Here you would just have to apply it over a small distance to get this to rotate up that way. So that's another way to think about how the distance increases. The distance here increases in this same way, this L2 over L1 thing, as what the distance here increases. So you're moving something a longer distance in order to avoid having to exert as much force. All right, so finally let's talk about pulleys. So the way the pulley works is by using multiple copies of the same tension in a rope or a cable or something to multiply the amount of force that's applied locally to some mass. So what the idea is that I pulley colon and then idea colon, so this is a little awkward. So multiply the number of times a given tension force, which you apply, you're the one applying this tension force. See, you're pulling on this end of the cable. So multiply the number of times a given tension force can be applied to lift a mass. Now, just to redraw this picture here, so the way you think about this from your perspective is that you have this cable, and so you pull, so you're pulling here. So you pull here, and this is with force T, and I'm calling it T for tension, and that's because that's going to be the tension in the cable when you're pulling on it. Now what happens with this cable is it goes over top of this big pulley here. And so it's wrapping around. And what that pulley does is it redirects the tension. So it comes down here. And now in this part of the cable, you've got the same tension. So you've got T here, you've got T here. Now here I've called it T1 and T2, but the point of the whole exercise is that the pulley just redirects that tension force. The tension will be the same in the cable at all points. Now how do you know that that's the case? Well, if the tension was different at different points, the cable would be deforming. It would be pulling apart. The only way, and you can think of that as sort of a force equals mass times acceleration thing. If I think of if I zoom in on the cable here, and so here's a little bit of the cable, and I think about just a little piece of cable here. So this is sort of a little bit of the cable. Well, if the tension force here at this end was bigger than what the tension force here was at this end of that little piece, then it would pull apart. It would accelerate. This part would have to be moving apart because there would be a net force. I guess a better way to think of this is the force. So here is the tension from this part pulling this little bit this way, and this is the tension from this part pulling it this way, different ways. There would be a net force on this little element of cable, and so it would move that way, and that would mean the cable would break. So as long as the cable doesn't break, you know that the tension in there has to be the same. That would be changed if there was some friction in the pulley, because it would sort of shelter this part of the cable from part of the tension there. So we're going to assume there's no friction in the pulley and that it will not mess with the amount of force. It will just redirect the force of tension around there. So I have the same tension here, and then this is going to wrap around a smaller pulley like this. So here's my small pulley. That's going to come up here. Now once again I have the tension force here, and this is going to come up and be attached to the center of the big pulley. And then from the center of the little pulley I'm going to hang a line. I'm going to put my mass here. Now in order to move the mass, the downward force being exerted here, this is mg, so this is the force due to gravity. So in order to compensate for that and then start to move this up, what I need is that the sum of the forces on here, which is this, so this force, the force here exerted on this line, that's this tension force and this tension force here. So I need 2 times the tension to equal mg. Now I can divide both sides by 2, and I can say, well, then the tension is just mg over 2. Now this is the whole point, because the tension is what I have to supply. See, I have to, so what the whole point of this is that now I only have to exert mg over 2, so I'll say force. Now I only have to exert force mg over 2, not mg. So that's the mechanical advantage. By using this pulley, I cut in half the amount of force I have to apply in order to raise that mass. Now, what's the expense? What's the trade-off in this case? Well, the trade-off is that when I pull on this cable here, it will shorten, it will pull this up. But so if I pull out a certain amount of cable here, half of that distance is coming from this one shortening and half is coming from this one shortening. So that means I have to pull out twice as much cable here in order to get this to raise up a certain amount. To say that another way, however much this mass moves up, then this little pulley will move up, and this distance here will be shortened, and this distance here will be shortened, but this distance here will be lengthened by both of those, by the amount this was shortened and the amount that was shortened, so twice. So the expense or the trade-off is you have to pull twice the distance. That's what the trade-off is. Now here I've drawn a picture to show that you can increase the mechanical advantage more than that. If you had to move a piano or an elephant or a hippo or something like that, one pulley wouldn't do it for you. You could only cut the force in half. You can use multiple pulleys. See this little system I've drawn here. You have the two big pulleys and then the two little ones. And in this case, the cable goes over and it wraps 4 times. You have this piece, this piece, this piece, and this piece. So you're going to have the same tension throughout the cable, and each of these tension forces is pulling up on this mg here, and on this mass here. And so what you'll get then is you'll get that 4 times, in this case 4 times the tension is equal to mg. And what that boils down to is, if I've written here, is the tension is only 1/4 of what mg is. So you only have to apply a quarter of the force, a quarter of the weight of that weight there in order to lift it up. Now the expense is that when you pull out a certain length of cable here, each of these little bits of cable only decreases by 1/4 that distance, and so that it only lifts up by 1/4 of the same amount. So it means you have to pull out 4 times as much cable in order to lift this a certain amount. And so you can repeat this as many times as you want to create more mechanical advantage. So that, I think, covers everything we need to know about these little machines.